Okay, so the first thing I need to know, I had a couple of confusions last time. The big confusion was that I didn't realize that Friday we don't have a class. And I thought we have 2 more classes and we only have this one as the last one. Because I'm away next Monday. So this is the last class.
This is last.
Yeah. Yeah, that's very sad. Yeah, I just wasn't aware that Friday we don't have a teaching, like the university is closed. So what we need to know about the exam assignment. So the assignment 4 is out already, even a correction of some typos. And I will also upload some old exams so you will know what to expect. And in the exam is without any open material, but I will have a cheat sheet with all the needed formulas. And I will also upload the cheat sheet ahead of time so you will know what will be provided during the exam. The other thing that's important to remember is that the exam, you are encouraged to ask questions during the exam. So I will repeat it at the exam, but just be aware that don't have to worry. You can ask anything you want during the exam. The worst thing is that I don't answer you, but I don't penalize you for asking. So as I said, I'm away next week, so I will not be able to hold office hours next week to prepare for the exam. But I will have my TAs hold office hours, and we will put on Piazza notices about special office hours for next week. Because the exam is Monday, not the next Monday, but the following one. What else? Solutions to assignment 3, I will also post them. I hope that TAs will post them within the next couple of days. So assignment 1 and 2 solutions are already posted, right? Right. So assignment 3 will be posted in a couple of days, and assignment 4 solutions will be posted after the submission. I think that's it. So okay, that was my first big confusion last time about the last class, and my second big confusion was about this. We said that the distance, we defined margin between a point and a hyperplane, and we said that the margin between a point and the hyperplane is the distance between the point and the closest point on the hyperplane. And all my formulas and calculations were fine, except that my drawing had a crucial mistake. The crucial mistake is that if this is a half space W, the vector W is the vector which is orthogonal to the half space. So the vector W is this vector. This is the vector W. If this is a half space, that's the vector W. And so all the worries and questions that I got last time were kind of better based than my answers. So now, when we realize that, it becomes very clear why. You remember that if I take the dot product of 2 vectors, u, v, so the dot product of the 2 vectors, we can think of it as if it is the length of the vectors, if it's the length of u times the length of v times the cosine of the angle between them. If I have 2 vectors, right, and I look at the dot product. So now, if the vector W is here, it is very clear why every point which is on the half space, so if I have a point x here, the vector of x is orthogonal to the vector of W. And therefore, for x on a hyperplane described by W, the dot product xW is 0. Because the vector W is the vector which is orthogonal to the hyperplane. And x resides on the hyperplane. Even if I take the dot product of two orthogonal vectors, I get 0. Right? And again, it also now makes more sense about why the dot product x, Wx, gives us equals the margin of x of W on x for when the norm of W is 1. Because what is this dot product? I mean, the dot product is, right, this is my vector. This is my hyperplane. That's the vector W that describes the hyperplane. So this is HW. This is the vector W that describes the hyperplane. Here is the point x. So that's the vector x. If I take the dot product, I take right. So if I take the dot product of these two vectors, then I get the projection of x on W. And the projection of x on W is the distance times the norm of W. So if the norm of W of 1 is 1, the projection of x of W gives me the distance. So all the formulas that I wrote last time were correct, but the pictures that I drew were all misleading because I kind of got confused and draw W as being along the hyperplane where it's orthogonal to the hyperplane. OK, so this is just for getting the geometric intuition. But we said formally, we know that the dot product gives me the distance between a point and the hyperplane. And if we have a collection of points which are labeled plus or minus, and I'm searching for a hyperplane to separate them, I would rather take a hyperplane that maximizes this margin, because a hyperplane that maximizes this margin is less likely to err on points that are generated by the same distribution. And maximizing the margin, which we saw was corresponded to my error, to minimizing my error with the hinge loss. Because the hinge loss penalizes me for points that, even if they are on the correct side, the hinge loss penalizes me for points which are close to the boundary. So if I want to minimize the hinge loss, I have to push my hyperplane away from the points. So minimizing the hinge loss makes sense in the sense that it maximizes the margin. So that was the main conclusion of the last lecture. Minimizing the hinge loss maximizes the margin. We can prove generalization bounds about it. And since the hinge loss is convex, we can do it efficiently. And that's the key to this basic algorithm of support vector machines. That given a sample S, the support vector machine algorithm is trying to find a hyperplane that will minimize the hinge loss with respect to S, which is the same as saying maximize the margin with respect to S. I will not repeat the formulas because anyway, we don't have time to get into it. What I really want to do in this last lecture, because we need to kind of squeeze the end of the course into one lecture, is to talk about three very basic algorithmic tools that people use in machine learning. So far, in terms of tools for machine learning, we already discussed one tool. We talked about the boosting. Right? So the boosting was a very simple algorithm. We described the boosting algorithm, and the boosting algorithm proceeds in iterations. In iteration I, you kind of reweigh the points and try to find the projection and the separation along this projection, and then you add all of them to get the predictor. So this is one very practical algorithm. Today I want to mention three other important algorithms and just give you the flavor of what they work like. So one is kernel methods plus support vector machines. So SVM stands for support vector machines. The second technique is nearest neighbor. And the last technique that I will mention are neural networks. OK, so let us start with the kernel methods, the support vector machine. So what the support vector machines give us when we talk about this kind of learning, hinge loss, minimizing the hinge loss, we can do it efficiently. But there is one big limitation of this method, that it only learns half spaces. Right? All of this method is aimed to learn a half space. And as we mentioned several times before, real training data is not likely to be linearly separable. And we know that our learning algorithm, the best that we can hope from a learning algorithm like the support vector machines that outputs a linear classifier will always have error which is greater or equal than the error of the best linear classifier. So if my data cannot be separated, the pluses and the minuses cannot be separated by a linear classifier, any such method cannot be expected to give me reasonably low error. So let us look at one example. So we are in this situation where we have an efficient tool. We have this hinge loss, which makes the problem of finding the best hyperplane computable in a fast way. So we have this efficient tool, but this efficient tool only learns half spaces. And the data may not be separable by half spaces. So I have these efficient tools that gives me a big error in case the data is not linearly separable. We want to take advantage of having such a nice tool in order and be able to handle data which is not linearly separable. Realistic data is not usually linearly separable. So what we're using is the idea of a kernel, and let me explain it by a very simple example. I think I mentioned this example before in the class. And so how can we overcome the limited expressibility of linear classifiers. Well, by limited expressibility, I mean we can only, if all I can do is find a linear classifier, my data may not be, I cannot find a classifier with small error. So we saw this example before, but let's repeat it with a new context. So we looked at this, the situation where I have points, say that this is my training data, and the points are labeled, say, plus, plus, minus, 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 plus, plus, plus. So if this is my training data, and I have pluses in the sides and minuses in the middle, there is no good linear classifier. Every linear classifier will make an error which is at least as big as this third half. Second third, not third half. OK. So how did we suggest to overcome it? We said, let us look at an embedding. So we search for an embedding of the data in a different space, such that in this different space, the data will become separable. So the idea, let's try to pre-process our data by embedding it 1D or 2D in the embedding? 2. Embedding it into a space in which it is linearly separable. So for the data that I have here, I can take every point x and map it to the point x squared. So now, after this mapping, instead of having those points on the line, I'm going to have new points, the embedded images of these guys. And the embedded images of these guys, x squared, are going to sit on this parabola, right? So this point is embedded here, this point is embedded here, this point is embedded here, and so on. I take every point x and map it to the point x squared. After this mapping, if I reconsider my labeling, what I get is minus, 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 minus. I didn't change the labeling of the points, and these points are plus. But now, suddenly, in this two-dimensional space, I do have a linear separator that separates the minuses from the pluses. So by extending it, by embedding my points into a higher dimension, I expanded or improved the ability of linear separators to distinguish the pluses and minuses in my data. Now, there are a few requirements that we need to make for such an embedding if we want to use it as a learning tool. So let me first ask you, are there any limits to it? Is it possible that any labeled data that I get, I will be able to embed in some space such that I will have a line separating the pluses and the minuses? Yes?
Just fit like some polynomial to it to
so, right, so basically, let me start with the extreme case. Basically, I can embed any data into a space that will separate linearly the pluses from the minuses. Because I can take my data, say it's complete mix of minuses and pluses, and I'll embed it like this. I'll only pick 2 points. I'll embed all the negative points into this guy, and all the positive points into this guy. And after this embedding, there is a very nice linear separation between the pluses and minuses. So what's wrong with this embedding? Why won't we use this? I mean, if you want to learn linear classifiers, take your data, embed all the points such that the minuses go to the point -1, the pluses go to the point +1, and now the classifier will always be the same classifier, just a zero classifier. What's wrong?
Its predictive power is pretty weak.
Right, its predictive power is very weak. The problem is that, I mean, it's not just for fun that we separate the pluses from the minuses. Our goal is that we will get a new point, a new test point. We want to predict a label on it. And now, if my embedding dependent on the labeling, when I will have a new point, I'll just be in the same trouble. I don't know whether this new point is going to be embedded here or going to be embedded here. So I need an embedding that does not rely on the labels. And note that the embedding that we had here, x goes to x squared, did not require knowledge of the label. I could do it also on the new point that I haven't seen yet. So the first requirement is that I need this embedding to be independent of the labels, to be determined just based on the instances, but not on their labels. Now I can ask another question. So is there always an embedding which is just based on the instances and will guaranteed to make every data separable? The embedding should not be based on the labels, but only on the instances. And the answer is yes, even if we require, as we should, that the embedding does not depend on the labels, we can still always have an embedding in which there exists a perfect linear separator between plus labeled points and minus labeled points. And the embedding is, what I can always do is I will take my data points and embed every point as a unit vector in a new dimension. So if I'll embed one point in the unit vector here, another point in the unit vector here, and I'll have as many dimensions as I have points. Embed each point of our training sample S as a new unit vector in what dimension of the space will I need now? If I want a unit vector for every point, what should be the dimension? The size of S. So it's R to the size of S. This is my new space. And the point is that if every point, now I'm not very good at drawing it, but let me try to draw only 3 dimensions. So, okay, that's 3 dimensions, and I have the 3 unit vectors. Note that no matter what labeling I give them, I can always find a hyperplane that will separate the minus from the pluses. if I have a collection of unit vectors, that was part of our proof that the visit dimension of half spaces was n plus 1 in dimension n. We showed that if I have all the unit vectors, I can always separate them by any labeling can be separated by a half space. So is this a good method for learning? Yes. Because what? Why? Yeah, right. But why? How do we see it from our? You're right. We are overfitting. And how do we see? How can we see it from our formulas? Our formulas tell us that the difference between the sample error. So we know that the true error LP of some h, which is my half space, is at most ls of the half space. What is going to be my sample error after this embedding? If I embed it such that everything is linearly classifier and find an ERM, what is going to be my sample error? 0. Plus a generalization term, right? And what is generalization term? The generalization terms look like the visit dimension of my space plus, you remember, ln 1 over delta divided by m. And some constant here. Now, if I pick a new dimension for every point of S, what is the dimension here? It's the size of S. So what do I get here? I get here m. And I divide it by m. So I get this term is the square root of 1 plus something. So my error term is 1. So this is a not very useful guarantee. It tells me that my true error will be at most 0 plus 1. So if we just use those bounds that depend on the dimension, and I embed it in such a high dimension that every point gets its own coordinate, then we get no guarantee. We were doing very well on the sample, but we get no guarantee on future data. Right? Yes?
So in this embedding, what would happen to new points?
Right. So another question is what will happen to a new point in this embedding. I need a kind of a formula for the new point. That's another very good point. But I could always represent the new point. What we can do in such embedding is that I have the sample points, and I want to embed them each in a different dimension. And the question, which is a very good question, how will I represent a new point? But one way of representing a new point is I have to represent it as a vector whose length is the number of points in the sample. So I can represent the new point by the vector of its distances from all the old points. Remember, every old point becomes a coordinate. So now I need to represent this point by a vector whose length is the sample size. So I can represent it by the vector which is the distances from all the other points. And that's a representation that we will use in some cases. So we do have a way of representing a new point, but the problem is that this formula will give us overfitting. So again, where are we? We want to use our machinery for learning half spaces. The problem is that some data is non-linearly separable. The remedy is we'll take our data, we'll embed it in some high-dimensional space. Hopefully, it will become separable. But we have to be careful about it. We have to be careful that we don't use the generalization altogether. And OK, so now this is something that we do carry out in this SVM learning. However, we cannot rely on this bound. Instead, we rely on a bound that I only mentioned without proving last time. So to get generalization guarantees when our H is the class of linear classifiers over a representation over data representation in some high dimensional space, we use a margin-based bounds. So instead of the VC dimension-based bounds that we saw before, we're now going to use a margin-based bound. And the margin-based bound, I think I mentioned it, I didn't prove it, is that we can show that if, namely, if H has margin gamma over a sample S, then we can prove that LP of H, the true error of H, is bounded by the empirical error of H plus a term here that instead of the VC dimension uses some rho over gamma square plus ln 1 over delta divided by m. The main term that I wanted to look at is this one, where rho is the diameter of S. So rho is just a scaling factor. It is the diameter, how far the points are from each other. And gamma is the margin. Because I can increase the margin artificially, because I can increase the margin artificially by scaling, right? So assume that I have these points here. These are pluses, these are minuses. Say I'm after the embedding, everything is linearly separable, and I have a half space here, and it gets some margin gamma. And my bound gets better when gamma increases. As gamma increases, this whole thing becomes smaller. So I want the margin as big as possible, so I can cheat. I can cheat by taking all of this picture and blowing it up. Just scaling up. Scaling. And I will get suddenly my point sitting here, my minuses sitting here, the half space is here, and my margin is bigger. How come that just scaling will improve my error bound? This is kind of a cheating, and that's why I have here this row. I'm only looking at the margin in its proportion to the diameter of the smallest ball that contains all points. So if I scale everything, rho grows at the same rate as gamma, and I didn't gain anything. So we can get bounds, generalization bounds, that instead of using the VC dimension, they use the margin. It allows me, it gives me hope that I have meaningful classification even if the dimension of the space is very high. I didn't prove this bound in the class, I just cited it, but the spirit is the same. And another important thing to notice about such a bound is that this bound depends on the distribution. Because it's a bound that is gamma is my margin on the sample, whereas the VC dimension didn't depend on the sample at all. This is a bound that depends on the properties of the sample. So it's kind of a different nature of a bound. Sometimes we call it luckiness bound. If we are lucky and we had a sample that we could separate with large margin, we know that we will predict well. OK, so let me recap where we are now. We had a problem that we had something good. Something good was we had a good algorithm that can learn half spaces efficiently with the hinge loss. So it is trying to learn half spaces with as large as possible margin. Then we said, OK, but the best that it can get us is an error of the best hyperplane, and that may not be good enough. So there was a problem. So now we came in a solution and say embed it into a high-dimensional space, then it may become separable, because you can express more separations when the dimension is high. But there was a downside. The downside was high dimensions means high VC dimension and low generalization. So now we have an answer to that. On the positive side, if we are lucky and we can get good margins, then we can overcome the curse of dimensionality in that respect. And that's basically what we are doing. But now there is another negative aspect to it. And what is the other negative aspect? The other negative aspect is that if I go into high dimension and I'm trying to compute the best hyperplane, then suddenly my running time is becoming very bad. My running time definitely depends on the dimension. I have to read my vectors all together. And what we really do in practice is we really embed data into spaces that are not only high dimensional, but they can be even infinite dimensional. So I cannot allow myself an algorithm that has to read all the digits of the embedded point in order to find the predictor. Yes?
In that formula, does dimensionality play a role at all?
No. That's what's so nice. A very good point. In that formula, the dimensionality completely disappeared. All I care about is achieving a good margin, and I can ignore the dimension. And that's what allows me to use embeddings into even infinite dimensionality.
Is the diameter of S in the original dimension?
No, the diameter is in the new dimension. Everything is in the new dimension. Otherwise, I will take S, which had small diameter, and will embed it very generously, right? So everything here is happening after the embedding. After the embedding, I look at the margin and I look at the diameter. OK, so this kind of saves us almost a complete solution in terms of sample complexity. If we are lucky and after the embedding we have good margins, we'll talk about this in a second. But we still have the problem of computational complexity. And for the computational complexity, there is a trick, which is called the kernel trick. And that's what turned SVMs into such a popular and useful technique. So what is the kernel trick? The kernel trick is based on the observation that when I want to find a good separator in this space, what we are trying to minimize, we are just looking at what is the optimization task that we need to solve to find a good linear separator in the embedded space. In the space to which S was embedded. So what is the task that we want to solve? we want to minimize the error, or we want to minimize the hinge loss over the sample. So what we want is to minimize over the vector W that we will find, we want to minimize some loss. And the loss had a specific form. The loss had the form which was the empirical loss, which was 1 over m. I mean, I can write here the loss, say the hinge loss or the 0-1 loss of the hinge loss with respect to the sample of H, plus we had here some lambda times the norm of W. I will explain it in a second, but let's look at the hinge loss, or the 0-1 loss. The 0-1 loss, it looks like this. It is 1 over m, the sum over I goes from 1 to m, of my loss of W on the point xi, yi. Right? That was my general loss, was the empirical loss was always just the average loss over the sample. And what was this loss? What was this loss? This loss, again, sum I goes from 1 to m. This loss was just either in the hinge loss, it was just the maximum of 0 and 1 minus yi times the dot product wxi. Right? Yes. What? Can you speak more loudly?
Oh, sorry. It looks like you're doing dot product with
Oh, the brackets, yeah. The brackets here should be, right. Thank you. Yeah. But here it is the dot product. Okay, now the point is that the point is that in order to compute this, I'm trying to find, here are my points after the embedding. I'm trying to find a large margin separator here. And I care about this dot product. It turns out that I can represent W. I can represent the vector W just in terms of the points. These are the points which are called support vectors. I can represent the vector of the space W. If this is HW, I can represent W in terms of the support vectors, which are the points of my sample which are closest to this half space. The points, I can represent every such W in terms of distances to the points of my sample. So W can be represented as sum W equals sigma alpha I f of xi. F is my embedding. If I have a vector, the vector W is a vector in this space. Here is the vector W of HW. If I have enough points here, I can represent every vector as a linear combination of these points. So this is just a very, very small piece of information we need from linear algebra. If I have enough points in some Euclidean space, I can represent every vector as a linear combination of these points. All I need is these points will form a basis for the space. And it turns out that I can always represent the vector of a separating hyperplane in terms of coefficients times the points of the sample. So I want to represent this vector in such a way, as coefficients times points of the sample. And these points of the sample that I use for the representation, they are called the support vectors, and that's why the name support vector machines. So this is just using the fact in linear algebra that if I have enough vectors, I can represent every other vector as a linear combination of them. Now, what did we gain from this? What we gained from this is that now if I want to look at this dot product, now the dot product Wxi can be rewritten as it's the dot product. W is some sum of alpha I f, or let's call it alpha j, f of xj. I want this dot product with xi. So I represent the vector W of my half space as a linear combination of the different points that I embedded for my sample. So this was just re-representing the vector W. Now I can use the properties of a dot product and say this is the same, by the linearity of dot product, this is the same as sum over j of alpha j times what am I left with in the dot product? Yes. Right, f of xj. And this is actually f of xi, because everything, this guy, is f of xi because everything is happening after the embedding. Everything is just f of xi, because everything is happening after the embedding. So I can represent my loss. I can represent the loss that I want to minimize as a sum of coefficients times dot products between the embedded points. Now, it doesn't look like I've done a lot. I just shuffled around, manipulated the formulas. But it turns out that there is something very essential here. And it's the point that in order to find a good separator after the embedding, I don't need to know what are the coordinates of the points. I only need to know what are these dot products. So in order to find a good linear separator, I don't need to know what actually the embedding is. All I need is this matrix. So I have here my points of the sample, x1 up to xm, x1 up to xm. And all I need is those m square values, f of xi, xj, dot product f of xi. All I need is a matrix of m square values, which is the values of those dot products, f of xa, I, f of xj. Because my calculation shows me that if I want to find a good separator, it's enough to minimize the function which only depends on this. So now, no matter how high the dimension is, in order to find a good separator, all my calculations are only done over this matrix of m square values. And it is independent of the dimension in which I embedded the data. Now, this has also a very clear intuition. This thing is called the kernel matrix. And I can think of f of xi, f of xj. I can think of this dot product. This dot product somehow tells me what is the distance between the image of xi and the image of xj. I had here a collection of points. I embedded them into some high dimension. And now after the embedding, I have here f of xi, I have here f of xj. And what I need to know is what is the dot product between them. And if all the points are normalized to be on the unit ball, this dot product just tells me what is the angle between them. So how similar is fi to fj? I can do all this embedding into the unit ball, into the unit sphere. And if I have here f of xi, f of xj, all I need to know is what is the angle between them. So what we are doing is we are now turning things on its head. Instead of first having an embedding and then saying, but all I care about in the embedding is this matrix, we start with this matrix. And we choose such a matrix such that the entries in the ij entry of the matrix will tell me, will somehow correspond to how likely it is that this point and that point get the same label. So instead of first having an embedding, then realizing all I need about the embedding is this matrix, I start with such a matrix. And I choose such a matrix that reflects my intuition about how close those images should be. How likely, the closer they are, the more likely they are to have the same label. So I'm building a matrix that tells me how likely are 2 points to have the same label. And then, if I have this matrix, I can translate it into an embedding and do SVM, and all my learning will only depend on the size of this matrix. So the learning is based only on what we call the kernel matrix, which is this matrix of I have here x1 to xm. And here I denote it by kxi xj, where kxi is meant to be the inner product, the dot product between their embedding. But I don't need to know what the embedding is. And we choose it, we choose k, this function that goes from x squared to r. We choose this function to reflect our prior knowledge about how likely are xi, xj to have the same label. So let me give you such an example. So the learning now starts by choosing a kernel matrix or a kernel function. Then we optimize, we find a W in such a way, only based on this kernel matrix. And if it corresponds to a separator with high margin, if we are lucky, then we have good generalization. And we can calculate everything, the margins, the arrow. We can calculate everything just based on those kernel entries. So maybe to make it a little bit more concrete, let me give you some examples of which kernels are being used. And the data does not necessarily have to start in a Euclidean space. So maybe the most clear example is the task of document classification. Say I want to learn a classifier that when you give it a document, it will tell you whether this document is about sports, or about entertainment, or about politics, or about science, whatever. And assume for simplicity that I'm trying just to find a classifier that will separate documents to two classes. So, I don't know, just one classification. Is it about entertainment or not? I just try to classify documents, and for simplicity, let's say we only have two classes. Now, the document is just a collection, I mean, it's a text, right? So I want to define a notion of distance between two documents, two text documents that will reflect the likelihood that they are on the same topic. So what we choose is we view X, we view every point as a bag of words. We view every document as a bag of words. So we represent a point by a vector over the full dictionary. So if I have a document 1 will be represented as a vector over all the dictionary. So it starts, I don't know what's the first word in the dictionary. What?
Aardvark. A-A-R-D.
A-A-R-D.
V-A-R-K.
V-A-R-K. What is it?
It's an animal.
It's an animal. Okay. This is the first coordinate. And in some place here we have chair. And in some further place, much further, we have table. And at the end of the thing, we have something like zinc or something like that, right? I have here a vector which is the whole dictionary. And how do I represent a document as such a long vector? At every entry, I put a count of how often this word occurs in the document. So this word is probably doesn't occur in my document, and this doesn't occur in my document, and this doesn't occur in my document. And say my document has a size, I don't know what, 2,000 words, and share appears there once, so here I'll have 1 over 2,000, and so on. So I represent this is called representing the documents as a bag of words. So I represent every document as such a vector. So I took my documents and embedded them into a space that has dimensions as the size of the dictionary. So it is like dimension. I embedded every document into a point in the unit vector to the power 50,000, which is, say, the number of words in my dictionary. Now, most documents will be represented by very sparse vectors. Most of the vector will be 0. There are very few documents that contain every word of the dictionary, right? But now, why is it? And we add more gadgets to it. I mean, for example, we minimize, we put some weights according to each of them. We put here a weight, W chair. We put weights on each word according to how informative is this word. Like stop words like and, or, then, they will get a very low weight because I don't really care about them. And words that are more significant in giving me the content of the document will get higher weight. So in advance, I also keep a vector of weights for all the words. Now, what is going to be the dot product between two documents? The dot product between the two documents tells me how many of the meaningful words are shared between these two documents. So if I have a training data, which is documents and classification, document 1, sport, document 2, not sport, document 3, sport, document 5, sport again. So all I care about is this matrix of dot products, which tell me basically how many significant words do they have in common. What fraction of the significance words are shared between these two documents? It's just a dot product between two such vectors. And then I am learning a linear classifier in this 50,000 dimensional space but I don't need to read 50,000 dimensions because all I start with is a matrix that tells me here are my documents, and here I have 0.01, 0.03, 0.1, 0, and so on. So I have this matrix, and all I need is the entries of this matrix in order to carry out a learning of a linear classifier in this 50,000 dimensional space. And the choice of the kernel is such that I used my prior knowledge. And my prior knowledge told me that two documents are likely to be on the same topic if they share a lot of significant words. So that's how I chose my scores of likelihood of the documents. So this way, with kernels, we turn the support vector machines tool, which just learns half spaces, into a tool that can reflect prior knowledge by choosing a kernel, and allows me a lot of flexibility because the kernels correspond to very high dimensional spaces. Yes?
Does that mean we can use a function k that's not a dot product without ever actually embedding our points or anything?
Right. We use the function k without ever worrying about embedding our points. All we do need some requirements about this matrix. There are some algebraic requirements about this matrix. It has to be positive semi-definite, which means all the entries should be positive, and it should be a symmetric matrix because I know that kxy is the same as kyx. So there are some algebraic requirements, but other than that, we don't have to worry about anything. We just start with the kernel matrix that we design according to our understanding of the relevant similarity in our problem. And then we carry out support vector machines, learning as if we are half spaces, because all the learning needs is those entries of the mutual, right? So the whole point is that we just write kxi xj. This is what we come up with, the designer of the algorithm. The analysis takes this and say, oh, this is actually the dot product between f of xi, f of xj. And I'm going to use this for learning. But this is just a part of the analysis. I never need to know what exactly this f is. The analysis does tell me if there is such an f, then what we are doing is actually learning linear half spaces, and we can have generalization bounds and so on. Yes?
Maybe this is a naive question, but so if we don't know the mapping
Right.
of space, so how do we then classify a new?
Very good point. How do we then classify a new point? But here, I mean, I don't take it completely arbitrary. I use some formula for this function xi, xj. Right. I cannot just take a matrix because I need to know how to embed a new point. But if I did this by counting words in the document, I know how to apply it to the new document. So I will always have, this will come out of a formula, not just a matrix of numbers, but a formula that I could apply to new point as well. That will be my kernel. So it will be a formula that can be applied to new points as well and reflects how likely are those two elements to have the same label. Yes?
So using the dictionary example, we constructed our vector by looking at our sample documents and picking the words that were important out of those documents?
No, it's not depending upon the sample. I mean, before you would look at the documents at all, you know that you have, for every word in the dictionary, you assign some weight according to how much information there is in this word. So if I have here the word and, the weight will practically be 0. But if I have this word that you gave me before, whatever, it will have a high weight because it is very meaningful. If it is in a document, it tells me a lot about the document. So I designed those weights in advance. Now I get my documents. So I designed this function k in advance. Now I get my documents. And now when I get the documents, I can, for each of them, calculate this function. Now, this calculation doesn't require me to know all of those coordinates, because I don't need to know all of the dictionary. I don't have to go on the 50,000 words. I just have to do a count of the words in my document. I go over my document and count each word, how often it appears. And I have a table that tells me what is the weight of those. And then I can construct this table. And with this table, I can do linear space learning, because our minimization task can be expressed as just a minimization of function of this kernel.
And so every time you, sorry, the matrix is, I'm having a hard time reconcile how the matrix is sample dependent, but you're bringing in a new data point and you have these weights.
I bring in a new data point. A new data point is a document. I take the new data point, and I just look at the words in this new document, count them, and I know how to represent my new data point. So I just have to read this document and do a count of the words in this new document. And it will give me the representation. Now I can calculate its dot product with every old word that I had before.
And so we've said nothing about whether or not the document is about entertainment or not yet.
No, we didn't say anything.
This is just the representation.
This is just a representation. This is just a representation. Now, if every point here will be labeled plus or minus, and we will minimize the loss, we'll find a half space and apply this half space to the representation of the new point. So again, we have some data at the beginning. We do representation. We get this data in this high-dimensional space. Here we learn a half space. Now we take our new point, look at its representation, and decide on which side of the half space it is, and give the label. Yes?
In this example, we're trying to find multiple categories. How does that relate to splitting the space into?
So let me just repeat a question. She's asking, how does this representation relate to splitting the space in two, right?
How does the problem of figuring out the content of a document?
Okay, so the main intuition is, we hoped that under our embedding, there will be a large margin separator between the pluses and the minuses. In order to achieve this, I want that points that are labeled minus and points that are labeled plus will have a large distance, which is a small kernel. So I start with what is my intuition about which features of my elements will cause them to have the same label or different labels. It is really a way of introducing prior knowledge. I choose a representation or a kernel such that my prior intuition is that those that are likely to have the same label, they have a big value here. They are very correlated. Those that are not likely to have the same label get low label here.
So for the document example, the two labels, you only have two labels, right? Would it be like entertainment or not entertainment? Or it just seems like there'd be more labels if you're trying to...
No. There are two different components. One is choosing the kernel and then doing the learning. Okay? When I choose the kernel, what I'm trying to get is that those numbers will correspond to how similar those documents are. The higher the number, the more similar I think that they are. If I did a good job, then when I embed them and look at the labels, if I did a good job such that documents which are very similar get a high value, then I'm likely to find a half space that will separate them nicely. Because in order to separate them nicely, I need that points of different labels will be separated from each other. Separate from each other means the correlation will be small. The kernel will be small. Does it make sense? Now I can apply, once I have a representation that captures somehow similarity in terms of a topic, then I can try to learn one half space that separates sport from entertainment. Another half space in the same representation will separate politics from I don't know what. Each separation will be a different half space. But they will all reside in the same representation that kind of measures the content similarity between documents. So the representation really depends on my understanding of the problem, and then the half space is about the exact classifier that you wanted. Yes?
How do you intelligently come up with the function k?
Right. How do we intelligently come up with a function k? That's a great question. And there is a big gap here between theory and practice. So in theory, we choose k that reflects our prior knowledge. In practice, now the sad story of what's happening in practice. In practice, there are some tools that you can find from the shelf that are available on the internet. And one of them is the RBF, radial basis function, RBF kernels. And the RBF kernels are kernels which are all of the same type. The kernel of 2 points, x, x prime, is going to look like e to the minus the distance in my original space between x, x prime, divided by some normalizing factor sigma. So maybe there is some constant here. And now I can play with this constant factor. It turns out, OK, so what does this kernel do? It looks very ugly. But what does this kernel do? It says if points are, this is a e to the minus the distance, which means that if this is the distance of x and x prime, and I draw here k of x, x prime, so if this is 0, I will get here something which is very sharply high around 0 and decays very fast as I go away from 0. Which means if the distance is very small, then I care about it a lot. The minute the distance is not small enough, I ignore the distance at all. Because the minute the distance is not small enough, 2 points which are at this distance, and I have no clue whether they're going to get the same label or not. I know the 2 points are going to get the same label only if they are very close. So this kind of out-of-the-box generic kernel, the only thing that you need to choose is your scaling factor sigma. And it basically tells you how close should points be so that you will be pretty sure that they have the same label. And that really depends on your problem. In some problems, point can be very small and still very close and still have different labels. In other problems, the distance is more meaningful. So this is kind of a generic kernel that you have in tools that are available easily online. And all you need to choose is sigma, so people try different values without thinking much about prior knowledge. Keep separate validation test data on the side and check with each value of sigma how well they're doing on the test data. So that's the real and dirty way that things are really being done, if you don't have any better knowledge about your data. Yes?
So this distance function, doesn't that kind of lose some of the power of SVMs? Because don't we need to evaluate every coordinate of x and x prime?
You don't need to evaluate coordinates. That's the whole point of the kernel trick. You escape the need to know about coordinates, and all the information you had in coordinates, you translated it into this kernel function. Now, this kernel function is pretty blind.
Okay. Oh, so it's not like the Euclidean distance. This is the
No.
distance as per our matrix.
Right.
Okay.
Anyway, what did I want to say next? OK, this leads me to, this is as far as I want to I have only 5 minutes left. Crazy. This is as far as I want to describe support vector machines. Let me just mention, so we will not have time to go into neural networks, although they are currently very popular. I just want to mention that this kernel is getting us very close to a kind of a very basic learner, which is the k nearest neighbor learning. So the idea of a k nearest neighbor learning is that you look at your sample, so you get your sample points. So these are my sample points, and they're labeled plus, minus, plus, minus, plus, minus. And then I get a test point. So what I do for this test point is I look at its nearest neighbor. And I will copy the label from the nearest neighbor. The k nearest neighbor says I will look at its k nearest neighbor, and I'll give it the label of the majority among its k nearest neighbors. So that's the oldest learning algorithm in the books. Even that's the simplest thing you should do. Just look at, do I have, when I want to classify, think of a recommendation system. You want to give a recommendation to someone about which movie is likely to enjoy, right? So what do? You look in your database of other people and which movies they enjoyed or not, and look for someone which is as similar as possible to the test point. And tell him, oh, you look to me like Jerry, you probably like the same movies as Jerry. So I'll recommend to you what he has. That's the nearest neighbor classifier. And this thing is kind of working in a similar fashion. It tells you you care about things only by how much closer they are to you. So that's a very basic classifier, and we can prove some guarantees on how it works. And the RBF kernel is kind of turning this idea into a kernel method. And I'll say two more. So should I say anything more about the k nearest neighbor? Let me just say one thing about the k nearest neighbor. K nearest neighbor, k and n, is guaranteed to converge to an optimal classifier for every problem. So this looks like magic. K nearest neighbor is guaranteed to converge to an optimal classifier on every problem that you have. Where is the catch? When someone tells you it is guaranteed to converge, what should you ask? Yes. Yeah, what is the rate of convergence? How many samples will I need to see before it converges? So that's the catch. And the rate of convergence, and it turns out that the rate of convergence depends, right, but the rate of convergence depends on the Lipschitzness of the labeling function. So what is this Lipschitzness? This Lipschitzness, I don't know if you've seen it in mathematics, the notion of the Lipschitz constant of a function. In other words, it depends on the likelihood, how likely are two close points to have different labels. So this is not a big surprise. The rate of convergence of k's nearest neighbor depends on how likely are two close points to get different labels. But the magic is that if you don't care about, if you have infinite amount of data, then this is a very good system to use. Sorry that this is the end of it. I mean, I realized I was going a bit too slow, so we didn't cover much. You're welcome to come to my next courses next year, and of course read the book, and come to me if you have any questions. Yes?
When are we going to be tested up until the midterm? Sorry, final.
You're going to be tested in the final only on the material that was covered by the assignments.
Which is up to last week?
Which is up to what is covered by up to last week. Say up to last week. Everything that was covered by the assignments is a legitimate question for and I'll upload all the exams so they will know kind of what level of difficulty to expect.
And what is the course following this? Is it a grad course?
A grad course, yeah. This is the 4th year, only grad courses follow it. Yes?
Do we have class on Friday?
What?
Do we have class on Friday?
No, we don't have a class on Friday. The university is closed. Yeah, it came as a surprise to me, but